Physics
Physics Bites,
a science podcast in English by the students of Nobel d'instruction.
So, hello again. So we're here for our last episode of the season. We have two students who did an interesting presentation on superconductivity. So I'm going to let them introduce themselves and then we can get started. So, you guys want to introduce yourselves?
Hi, I'm Aurore.
And my name is Kelly.
So we have Aurore and Kelly, who are two students in their final year of secondary school. You guys are both doing physics this year, if I'm not mistaken.
Yes, we are.
Yes, and you're both doing biology also, or you're doing math on the side, and you're doing both of you are doing math.
Yeah.
There we go. So both doing math and physics. So you guys have seen more physics than, let's say, half of the other classmates who have already had their admission. But let's get to the topic. So superconductivity, which is a very interesting topic, which is very currently being debated and has a lot of potential for the future. So do you guys want to start maybe talking to us about what you presented, maybe a bit of a history, some basic concepts of it, and then we had a few questions from your classmates, not as much as usual, but we'll chalk it up to the fact that it was a pretty advanced topic. So
I can start with the history. So we found that scientists need to have a conductive material in order to make the electronic flow through. But the conductor loses energy when it goes through in light and heat, depending on individual materials' electrical resistance.
And this was called, we learned this in many years ago when we were in junior high. And
Joule effect.
Right, the Joule effect, which is basically because of the resistance that the conductor always has. Even if it's a little bit of a resistance, it causes a dissipation of the energy. Go on.
Yeah. And so they found gold and copper. And they found a direct relations between temperature and resistance. And that means that the colder the material is, the more conductive it becomes.
And so the less resistance it poses to the passage of the electric current. So the colder it gets, the less resistance, so you lose less energy.
Yeah, okay. But no matter how cold this material was, they will always show some resistance. And so in 1911, a Dutch physicist discovered that when mercury was cooled all the way down to 4.0 Kelvin, below absolute zero, his resistance...
above absolute zero.
Oh, yeah, yes. Above absolute zero, his resistance disappeared and it was the first superconductor.
Right. Do you have the name of the physicist who did this? Do you remember? I don't remember the name.
I don't have it right now.
Okay. So this is 100 years ago. This is more than 100 years ago. So the first example of what you call superconductivity, which means that electricity flowing without any resistance, dates back to 100 years ago.
Yeah.
And you're saying it's directly related to the temperature of the topic, of the subject.
Yeah.
Now, 4 Kelvin, is it very cold?
Yes, it is.
How much is it in Celsius? How cold is it?
Oh my god, I don't know, but I know that Celsius is...
I know,
is
it's
almost
270 below zero Celsius.
Do we see temperatures like this at all in our daily lives?
No.
So I guess the only place where temperatures would go down this cold would be in outer space, right?
Yeah.
Where we think the average temperature of the space when it's not exposed to the sun is about 4 Kelvin. So it's not something we can have in our daily lives.
No.
Okay. So Kelly, I think you were going to add something.
Then we talked about the theory behind all of that, which is the BCS theory that was invented in 1972 after John Bardeen, Leon Cooper, and Robert Schrieffer.
Right. So these are the three physicists who got the Nobel Prize for their explanation of the theory of superconductivity.
Yeah. And since it is explained by quantum theory, we didn't explain it further, but we explained the basics of it. And basically it uses Cooper pairs and it ensures it to have no resistance. So basically superconductivity is below a certain temperature that we call critical temperature. There is no resistance in the material, meaning that there is no loss of energy, like you said.
Right.
And yeah.
And during their presentation, you gave us a very nice, interesting diagram about what these Cooper pairs are, which is going to be very difficult to explain, I think.
I can't explain it without
Right, it would be very difficult, but that's, I think it was the key discovery that helped explain what's happening at the quantum level with this. Okay. What else did you guys talk about in your presentation?
We talked about the applications of it, the advantages, the disadvantages, and
So we'll come back to the applications maybe later.
Yeah.
Can you give us a bit of information about how things have evolved so far since the 1950s? How much? Because we're doing a lot of work on superconductivity, and what is the aim? What is the ideal goal we want to reach with superconductivity?
I think that superconductors are very useful in our daily life for many reasons. And they could allow us to transform the electrical system, for example, because our current grid lines are not under the ground,
Right.
which takes a lot of space, and having a superconductor power grid lines could allow us to lose less power and could take
So the idea is
less
that
space.
anytime we can use electricity without losing energy because of the Joule effect,
Yeah.
or because of any form of resistance, well, that's ideal. That's what we want, right?
Yeah.
Because energy lost means we have to produce more energy somewhere else, which probably has more greenhouse gases, more pollution. So if we can actually have electricity with no resistance, well, it's kind of the holy grail, right? Like then we can do pretty much anything with much less energy. So the dream is that. So what have scientists been trying to do ever since the beginning of superconducting? So the first superconductor, you're saying, was at 4 Kelvin.
Yeah.
4 Kelvin in daily life is very difficult to maintain or to use, right? But all the research that's been going on, besides the theoretical part, is to do what with superconductors?
Yeah, we're trying to have a superconductors that have a critical temperature which is quite high,
Right.
so that we can use it in our daily life without
Right,
using
right.
super, cooling things.
Yeah.
Below-
What we call room temperature,
room
or high
temperature,
temperature superconductors.
And so there isn't any natural superconductors that have this high temperature. We only have some alloys that are cuprates, and so we are making them, and they're not natural.
So there is no one element that is superconductor. You have to mix different metals to have superconductors so far.
There are natural superconductors like copper or things like that.
So you can have an ordinary metal like copper
Yeah.
behave as a superconductor,
Below it, it's
but
going-
only if it's really, really cold.
Yes.
So if you want to go to temperatures higher than 4 Kelvin, which would be pretty much necessary,
Yeah.
you can't depend on any one metal. You have to mix stuff. You have to have
Yes.
what you call an alloy, which is
And
either a mix of different
the most
metals.
common are cuprates.
Right. Okay.
And about the superconductors, the ideal one must be composed of naturally abundant atoms, easy and cheap to produce, and as Kelly said, with a high TC. And
TC being the critical temperature where it
yes,
goes into
yeah.
I see you guys are so expert in the field, you're just using acronyms like that. So the idea would be, so we measure how useful, I guess, a superconductor is by the TC, which is the critical temperature.
And with also if they're abundant or not on Earth.
Right.
And
So if we can have like a really high TC, but it uses stuff that's very difficult to obtain, then
It's
that's very useful.
Really, yeah.
Okay. Do you guys know what is the highest?
Yeah, I know.
Yeah.
It is a sort of cuprates, like I said before, and I think it reached 140 Kelvin.
Which is still pretty cold, which is still minus 100 and some odd degrees, but much less cold than.
It is much better than like 4 Kelvin.
Right, which is very, very difficult to obtain. As a question, just on the side, this Dutch scientist who discovered the first superconductor, how did he produce a 4 Kelvin temperature? Do you guys know? That's not very easy to do. You can't put that in the fridge, right?
I guess with liquid nitrogen.
Okay, right. Because liquid nitrogen is one of those gases whose temperature can go very, very low and still remain liquid. So you have to cool it down into these temperatures. Okay. Anything else? What else did you guys talk about in your presentation?
I also talked about the Meissner effect. I
Ah,
also
the-
talked about the Meissner effect, which is the effect that we see, on the social media when the sort of
Right.
magnet starts to fly.
Right.
And
Which is the classic example that we
Yeah.
always show when we
The-
want to talk about. Can you give us a little idea what the Meissner effect is?
yeah, basically the Meissner effect is the magnetic lines of whatever magnets that are repelled by the superconductor below its critical temperature,
Right.
and therefore it's.
And why does this happen? Do you know why a superconductor does this? But so the classic image is like a little tiny block of metal,
Yeah.
and then it's cooled down with liquid nitrogen, and we can see it floating above a magnet or something like that, or a conductor. Why does it do this? Why does these electric lines push it away in a superconductive state, but not in a normal state?
I think I saw that there was eddy currents that formed in the superconductors
Right.
when it is below its critical temperature, and with the electrons flowing in a certain way,
Yeah.
it kind of replicates the magnetic lines of
Right.
the magnet. Just
So somehow it
bonds.
becomes polarized in the
Yeah.
opposite way, and so you have this repulsive force.
Yeah, that's why.
Okay. Okay. So the Meissner effect, do we use it in anything, or is it just for showing little kids and getting them interested in science?
Actually, nowadays it's not really used because it's very difficult to achieve because of the 4 Kelvin temperature needed. But in the future, scientists would like to apply this technology to different things like maglev trains.
Right.
Maybe you've seen it in movies, trains that fly above
Right,
the
they
rails.
sort of float over the
Yeah.
rails. All right, so how about this? Do you guys have anything more that you want to talk about that you talked about in your presentations? And if you don't, we can go on to the question part.
I can just add that the
Sure.
the BCS theory that I
Right.
mentioned before, it doesn't apply to every superconductors actually.
Ah.
There are some superconductors that we created, which are the alloys, that don't obey to this BCS theory, and we still don't know why they act like superconductors.
Ah, okay. I did not know this. So basically, BCS theory being the theory that
Yeah.
explains why superconductivity even happens. And you're saying we've observed
Superconductor.
certain alloys which behave like superconductors, but
Yeah.
not because of the reasons given
And
by
these
BCS
are
theory.
called a type 2 superconductors. I don't know if you've heard of it.
No, I have not.
So there is type 1, which is a little bit...
The ones that are explained by BCS? Okay.
Yeah, and then there's type 2, which is we have higher temperature, higher
Right.
critical temperature, but they have like different property. For example, for the type 1 superconductors that I
Right.
explained, they have also a critical magnetic field,
All right.
meaning that they have a really low critical magnetic field, meaning that when the field is too high, they kind of break and they are not superconductors anymore.
Ah,
Yeah.
okay.
And so for the type 2, they have a higher critical magnetic field,
All right.
meaning that they can support more.
Yeah.
But then they can let some magnetic field pass, and it depends on the superconductor.
Okay.
Yeah.
So, if I understand correctly, you're saying for the type 2, these ones that don't are not explained by BCS
Yeah.
theory, they have a higher TC?
Yeah.
So they're actually more useful for where we want to go with superconductivity than the
Yes, most
original
of them.
kinds. Okay. And we still don't know why they behave that way.
No, we don't know.
That's very interesting. All right. So, how about we move on to the question and answer period?
Yeah.
Okay.
So I think one interesting questions was the one by Ellie and Alexander.
Yeah.
What is the future of superconductors? It's a very basic question, but
Yeah.
it's really important
Yeah.
because the future of
Right.
a new technology.
So, in terms of where the research is going, or where the applications are going, or both?
I think the second one. The
Okay.
application.
Let's talk about that then. So, before maybe we get to their question, can you tell us if there are any applications of superconductivity that we use already in our daily lives?
And so we have an MRA scanners.
MRI.
MRI, yeah. MRI scanners.
So MRI is magnetic resonance imaging. This is one of the imaging technologies we use to sort of see inside the human body with a lot of precision.
Yeah, so superconducting magnets are used to produce a large uniform magnetic field inside the patient's body.
Right.
And the MRI scanners, which contain a liquid helium cooling systems, capture how these magnetic fields are reflected from organs in the body.
Right.
And so we could see if there is disease, cancer, or other.
Well, how what changes it? So the principle of the MRI machine is very interesting. It's that so you have these magnets, like you said, which create a very, very, very powerful magnetic field. That's why you need superconductors, because you need very high currents to produce high magnetic field intensity. And to have high currents without burning everything up, well, you have to have no resistance. That's why you need the superconductive properties. And then they create this magnetic field, and that sort of plays around with the magnetic fields of the particles inside the body, and when they come back, they produce a current, and then you can use that to sort of create an image. So you said liquid helium as opposed to liquid nitrogen. Why liquid helium, do you know?
Because it is lower, the
Yeah,
temperature is
right,
lower.
because
it is
liquid
like 4.2 Kelvin.
Right, so liquid helium is even colder than liquid nitrogen. So which brings us to an interesting point in that most of the uses for superconductivity are often for magnets, when you want to produce really strong magnets. What other application in science do we have, do you know, which uses superconductivity and really powerful magnets?
I think we have high sensitivity particle detectors, for example.
Okay, yeah. So a lot of stuff linked to particles in general, whether it's detection or other things. Kelly, you were going to say something?
Wasn't it the...
Yeah?
Tokamaks, I think.
No, that's for fusion.
was it CERN? No,
Right. Yeah. What do we have at CERN that's very, very famous? The LHC. Somebody in the audience. What do we have in CERN?
Josephine knows a lot.
Right. So we have a particle accelerator, right? And a particle accelerator basically is used to create very, very fast-moving particles, and then they hit each other, and they sort of blow up in little tiny quantum explosions, and we can observe what's going on, and that helps us understand many things about them. And the way we can accelerate these particles is with very powerful magnets. And these powerful magnets are, like Aurore was telling us, powered by superconductive materials, so you can have very high currents without actually reaching any danger with fire, heat, etc. Any other applications that we have in our daily lives of superconductors? Do you guys know?
In daily life, I don't know.
Not necessarily in our daily lives in that, like, you know, we're using our telephones. I have a superconductive telephone, but, like, I mean, stuff that we use.
For all the phone, the superconductors help to improve the efficiency and the reliability of cellular phones, which requires high frequencies.
Okay.
Because these frequencies are very difficult to achieve, but they were easily achieved with materials with superconductors.
Okay.
And so this technology appears in many cell phone receiver towers, and more and more.
Okay, I didn't know that. Okay, that's very interesting. At one point, you guys mentioned also maglev trains. This was those trains that sort of float. Do they use superconductors or no?
I guess yes. Because of the Meissner effect, so you can fly.
Yeah.
Because can we also do that just with magnets?
Nope.
No, you can't. It hasn't enough power.
So you can't just have trains that are sitting on big magnets. You have to create the magnetic field, and to create magnetic fields that are strong enough to push up a train, you're saying we need superconductive materials? Okay.
Because trains are very heavy, so if the magnetic field isn't
strong enough, then it won't have. Okay.
And, for magnets, I don't know if you play with it, but they don't stay on each other.
Yeah, but that I think we can sort of fix it. Maybe the way, the shape of the sort of magnets that you can construct. I suppose that's more of an engineering task, I think, than a physics task, maybe. Any other applications? Did you guys find anything or?
We have ray gun and coil gun magnets.
Right.
So
again, the idea is that usually superconductivity, we use it to create magnets, basically.
Yeah, because with the Meissner effect is easier than with other magnets.
Okay. So there was one question. So Eddie and Alexandre, which were one of the few students who actually asked any questions. They had another one about magnetic fields. So, do magnetic fields pose a danger for human health? Did you guys find anything on that?
Yeah. So,
So, Artie, before we talk about a strong magnetic field, a weak magnetic field, is that dangerous?
nope.
It won't.
We know it's not dangerous because the Earth has a weak magnetic field.
Yes.
We live in it, and we seem to be doing all right.
Yeah, in your daily life, we have a lot
Right.
of magnetic fields, but it's not dangerous.
Okay. All right. So we're kind of running out of time. So let's get to maybe one final question. Is there any one question that you guys wanted to come up with, or maybe because I think there was a question about if we're ever going to use superconductors in our daily lives in a more wide way, or there was a question about just the whole cooling technology.
Yeah, I can talk about the cooling technology.
Okay.
Because
Some of that
it is quite low. The 5 Kelvin is quite
Very, very low, yeah.
complicated to reach, and so basically we use liquid nitrogen, which has a low temperature below 77 Kelvin. Then there is also liquid hydrogen,
Yeah.
and the liquid helium, which are below 20 and 4.2 Kelvin.
Yep.
And then there is also a laser that is used
Yep.
to cool quite near the absolute zero, but
Yeah.
not yet.
But it's different. The way it functions very different. But
Yeah.
yes, we also use laser for cooling. Yeah,
But it
ironically,
is
yeah.
much more expensive as
Yeah.
well. So
Uses more energy.
Yeah, and liquid helium is also a little bit expensive, I think. Which is that's why we use liquid nitrogen.
Yeah,
because it
much more abundant.
Yeah,
And the problem with liquid helium also is that because not only is it very
Very
cool,
dirty.
it also is what we call a superfluid. A superfluid is a fluid that has no resistance, and that has its own problems. There was a whole story with CERN, LHC when it first came online, and but we won't get into that. But it was very interesting because one of the problems was because of liquid helium, it was able to go through one little crack, and that caused a problem. All right. Well, thank you very much for your interesting talk on superconductivity. So this finishes our first season of Physics Bites. We're going to have a few more episodes coming from the grade 11 students called Physics Bits, which are much more short and about scientists. And maybe next year we're going to hopefully come back for season 2 with our grade 12s from next year. So Aurore and Kelly, thank you very much for your interesting talk on superconductors. And we will see you next time. Bye-bye.